a scientist from ISRO. His expertise is mainly in the X-ray observations of the solar atmosphere, on which he will be speaking today. He will also speak on one of the X-ray payloads on Aditya-L1, which is SOLEX. Okay, Srikar, please.
Hello and good morning to all. So am I audible to the ones at the back? Yeah, this is fine. All right. So yes, as sir mentioned, I'm Srikar. I'm from the Space Astronomy Group of URSC Satellite Center, and I've been involved in Aditya for like last 5 to 6 years, and been working in 2 of the payloads, not just in the SOLEX but also in Helios and magnetometer as well. So yeah, so based on what we have done and what observations you can expect from Aditya, we will try to give an overview of what observations have been done already, because this is not the first time that people are looking at sun in X-rays, and why we want to do that, and we will go into much more details of it. And yeah, as we so this all right. So the title of today's talk is X-ray observations of sun. Pretty generic one, but yeah, I'll try to keep give the specifics of if you're interested on the details of what instruments you can expect. So I have actually divided into a 3-part talk, so that it will be clear into what sections. I wanted to do it in 3 sections. The first part we'll do the basics. I didn't take I have no knowledge of what your backgrounds are or what your expertise is. So I'll start with the basics. If it is already known or something, if it is repetitive, please let me know. I can dynamically tune my talk. But yeah, first part will be the very basics is why X-rays. I hope X-rays and the observations of X-rays and related aspects of solar physics have not been covered in the in this previous talks of the workshop. So I am hoping that this will be a new thing to you, and which phenomena which can study. When we say what are you doing when you're looking at X-rays, so, like people know usually, when you say X-rays, the first thing that comes up in mind is what? X-ray. Correct. Yeah. So yeah, you're getting your body scanned for X-rays and stuff like that. So essentially, to find out if there is something wrong with the skeletal structure of our body, X-rays. So what can we observe? Can we X-ray sun? I mean, I'm just trying to keep things normal. So can we X-ray sun? Is that something same as what? Of course, it is not the same, but yeah. So what phenomena we are trying to study when you're saying we are looking at X-rays, and what are the processes at work? Basically, the physics of it. I mean, what processes will give emission in X-rays, and how to understand them, and what is needed to study them. So if you know a particular process is happening, we'll come to it. I'm not giving any names yet, but it's just a prelude of what this section of the talk will be. Then we'll go into the physical mechanisms, what gives rise to. So it is pretty much your atomic physics. What gives rise to is because it's essentially a ball of plasma, need not be fully ionized. So we'll go through each section and then see which physical mechanism that we know of already is actually taking part at the corona, or let's say chromosphere of the sun, and find out how we can link them back to the observations that we do. So that's where the second part comes about. It's the measurements. Now that we know that, okay, if I study X-rays, if I study sun in X-rays, there can be some expectations that we have in terms of what the physical processes that are there. But for that, what type of measurements are needed and what can be done, when I say I want to study or observe in X-rays. So I'll talk about few of the techniques. So I'm sorry. Yeah, so the techniques will be different techniques. So this will be, I hope this will give a flavor of both the instrumental aspects as well as to, so if you're getting into the instrument building or development aspects of your research later, it'll be very interesting to find out how do you detect X-rays and what are the different mechanisms that you do it and what are the different ways in which you can do it. So I mean, these is sort of the exhaustive set, but yeah, I'll try to see if there is something that new dimension of it comes up. So there are different dimensions of techniques. So you image and then you do spectroscopy, you do something called timing analysis, and then there is something called polarimetry. So these are, if you have gone through any of the astronomical instrumentation courses in your undergrad or postgrad, you will definitely see that these are the four dimensions of instrument development or instrumentation observation. So imaging, spectroscopy, timing, polarimetry is the standard for not even just solar physics, but also for astrophysics in general. So what can we do? So that covers the second part essentially. So now we would, when the first part gives us the essential basics, and then what measurements can be done and what measurements are done till now. So it's like a regaling of a history sort of that. And the third part is, yeah, now that we are here at this point, up to in 2023, and X-ray observations have started, they are contemporaneous with the space age. So you find out, yeah, we'll come to that, why we have to go to space. But yeah, so there have been several decades of observations till now. This is not the first time that people are doing observations of sun. So what can be expected from Aditya-L1? That's one of the things that we will discuss in the third part. And then the X-ray instruments on Aditya-L1 are spectrometers. You get to know what they are and how they, I mean, what you can expect from them. So we will dwell some time during this part actually on the X-ray spectroscopy and how to do it and what results that have been that are available already. So what is the current level of understanding we have? You would have heard of RESI and other instruments already. So X-ray instruments. If not, then we will go through a few of those instruments and we'll find out what are the results that we have already accrued over the years. Basically, the knowledge base. And then is that the end of it? I mean, if you have, aren't there any outstanding problems for you to solve, the next gen guys? Yeah, there are. Yeah, there are. We'll try to give a very brief outline of it and then end with the future prospects as to what you can look forward to. So that's a very long outline of the lecture. Let's jump right into the first part. This is, yeah, nothing new here. Just wanted to highlight this aspect. So our domain of today's talk, as you can see, as I said, X-rays is this region, the soft and hard X-rays. So the thing that I want you to look at is the energy range and then the wavelengths. So we will be interchangeably using these wavelengths and energies because, yeah, some community uses the wavelengths and some community uses the energy. So, but if you're a high energy astronomer on a solar guy, high energy solar physics guy, then you would mostly be dealing in what you call KEVs or EVs. So the energy scale is so we are talking about the energy range of, let's say, 100 EV. And beyond that, we'll say soft X-rays. That is this region. And by the time, it's not a very hard distinction here. Pardon the pun here. So hard X-rays actually start from 10 keV, but it is just a convenient definition. Nothing physical about it. So this is our energy or energy range of interest, or wavelength of interest, or frequency of interest, or temperature of interest. So what we are looking at, what are the temperatures? So this temperature is essentially the temperature that is converted from the energy. So if it's just a translation from kinetic energy to the velocity, and that's how you associate that velocity to a temperature. So it is it's not the brightness temperature. So you can see that the temperature is yeah, very high. I mean, 10 power 5 or 10 power 6. So we are actually looking for something that glows at 1,000,000 Kelvin. I mean, now you know where we are going. So essentially, we will be looking at corona of the sun when we are saying we are doing X-rays. So why not? Because all other temperature ranges where the sun emits, let's say the photosphere or so, let's say 6,000 Kelvin, have their emission peaks around this point. I mean, even if you consider a black body radiation which is in thermodynamic equilibrium, then you'll see that the peak of the solar photospheric emission happens to be somewhere in the optical region, just like this plot shows, right? The 6,000 somewhere close to the left side of the optical region. But that is not what we want to see. We are actually looking to a very high energy and high temperature region, that is the X-rays. So yeah, this is something that I want you to keep in mind, and we are extending our domain up to, let's say, I will not go into the gamma ray part today, because though they are very closely related, the X-rays and the gamma rays. Can someone, just to wake you up, can someone tell me the difference between X-rays and gamma rays? They are photons, they are high energy photons, but how they are different? Okay, it's a photon matter interaction. Something more specific? Yeah, origin. What is the origin? So everything has an origin story. So what is the origin story of X-rays? I mean, anything. Just what? Yeah, that's interaction with matter is one thing that is pertinent. But that is the post-birth part. Once they come out, they'll interact differently because if for that matter, optical interacts differently with from X-rays with matter. So what is the distinction? That is one thing. The main thing is generation itself. X-rays are generated from electronic transitions in matter. We will discuss what brings up X-rays in detail, what comes about when we say what we are looking at. And gamma rays are nuclear interactions coming from nuclear interactions in matter. So that is the first thing that I mean, it's most people would not say it, but say gamma rays or X-rays. Yeah, and there's no hard and fast hard distinction between these, except for that they are all high energy photons, but their origin is different. So if you give me a 100 keV photon, no way we can tell whether it is an X-ray or gamma ray, unless we know where it came from, right? But if we go to softer part, or okay, one more just aside is why they are called soft and hard. Any guesses? Why? I mean, this is a distinction. It is not so, as I mentioned, it is not so strict, but around 10 keV we switch to, we're saying it hard, and then below that we say soft X-rays. Any guesses? Here, someone, sorry, correct. Penetration in matter. So it has actually come from the X-rays that we initially talked about, imaging of human imaging of X-rays. So anything that stops in the soft tissue is soft X-rays. Anything that doesn't stop in the soft tissue and extends to hard, which is bone, hard tissues. Hard tissues are bones are called hard tissues, and all the flesh and the muscle are called soft tissues. So in medical parlance, the low energy X-rays are called soft X-rays, and high energy part are called hard X-rays. That is how the term has come about. So I mean, it's just trivia, but it's good to know the semantics of it. Right. So that is where we are. So where we'll be mentally living in for the next few hours is this region. And let me just move on to sun. I'm pretty sure you have seen this profile. So this gives us the temperature profile and the density profile as we move about from the altitude of the sun. On the very low heights, we'll call it photosphere. It's not a surface, but it's a very thin layer from where the radiation from within the sun in solar interior can escape, and and that is where the opacities change, and that is where we call that is where we start to see a distinct boundary. It's not a very hard distinct boundary, but it's this region. So the entire region is photosphere, and it has this temperature profile, which is, as I said, 6,000. This is I don't want to spend time explaining this plot, But what I want to show you is here is that we said X-rays observations, I means they have an intrinsic temperature of 10 power 5 or 10 power 6 million Kelvin. I'm sorry. So you look at the temperature plot. This is 1 million, and when you hit the plot, you onto the x-axis, we see that it is hitting the corona. So all the X-ray observations are at best starting from transition region to corona. So that is, so when we are saying we are observing things in X-rays and we are doing some solar physics, we are essentially doing solar coronal observations. So we will try to understand how solar corona works by looking at X-rays, which otherwise we may not be able to do with other wavelengths. I'm not canvassing for soft X-rays in general, but here it's not trying to sell out this part of the wavelength. But definitely, yeah, it is one of the regions which promises the studies for solar corona. And also the other point I wanted to make is the densities. You can see this is the Ne is the electron density and this is the proton density, or rather hydrogen density. We will, because we don't know whether it is ionized or not at this point. So as you go away in the from the solar surface or photosphere, you'll see that there's a steep fall. And the transition region, yeah, it's a very nice plot, that clean plot that is shown here. That transition region is actually a very thin line. Believe me, this is the best representation, the smoothest representation possible. We know much less than the transition region than there is. So it's actually a much fuzzier region. See, it's a very non-linear kink that's coming about both in temperature and density. Something fishy is happening there. So there have been many attempts to do science for this region from many missions, but still, yeah, the actual how it is spiking up to these rates is fully not known. At least, yeah, at least not to the extent that we can convince everyone. So the steep fall in the energy density, rather the number densities of the electrons and hydrogen, actually tells us something. It tells us that the opacities and the interactions will in the coronal region are actually can be considered optically thin. So the optical depth is much less than 1. So any radiation that's coming from those depths will not be attenuated, or basically optical depth. What can someone tell me what optical depth is? Yeah, optical depth. Yeah, correct. So some column, take some column of with some Ne, number density of electrons, because that's the simplest that we can put. Just think there are free electrons, a column of electrons. Now if there is some radiation, I'm not specifying it is X-rays or anything. If any radiation, some photon that's going through it, what you can expect here? That is essentially, as he is mentioning, it depends upon the absorption coefficient. We will ignore the emission part. It's only the absorption coefficient of this and the distance that it travels. So optical depth is an integral. Essentially, the definition is integral of the absorption coefficient times the depth or the thickness. Yeah, you can see that integral. You'll see that dl. So alpha is the absorption coefficient of it, and if it's tau. But how do you visualize it? Yeah, the visualization part is if I send something I naught and out the intensity or the, let's say, number of photons. So simplicity, number of photons that come out of it is I or I, and the ratio, if tau is 1, optical depth is 1, it falls down by 1 by E. So when we say it is much less than 1, is, yeah, proportionately it comes down, and or it doesn't. So what we are saying here is corona, or the regions that we are looking at, are optically thin. So the attenuation is minimal, and that is one of the reasons why we call photosphere photosphere, because all the optical photons or even the IR photons coming out they have to pass through this region, right? Anything that's coming from surface, they have to pass through to reach us, right? So when they do, don't they interact? Can they interact with these number densities, right? It is like any if you've done any LIDAR experiments or something, if you shoot anything up, then there's some atmosphere that has to interact, and then it'll come down. So eventually it'll hit the ionosphere and come down. So something like that. So it is, whether it is coming down, if it comes down, it basically is going back to the surface, right? So we will not be able to see any photons. But that's not happening. So I'm only trying to emphasize the fact or the idea that a lot of radiation that is coming out of the solar surface, from that there is very minimal attenuation of that, even in spite of lot of material and lot of temperature transition that are happening here. That is what you are calling as optically thin. And that is where the region of that is where the other parts of the mechanisms come in. So what are the mechanisms of these processes that we'll talk about? Right, when we say we are looking at corona and doing this X-ray observations, what is it that we are trying to do? The main thing that we are trying to see, at least in this as a solar X-ray observations science, is doing the observations in solar flare. It's not just the one, but it is the one that mainly concerns us, because solar flare essentially it is a coronal phenomena and eventually transports or translates into different regions. I have a schematic picture of it, but its starting point is in the corona. And you can see, I'm just trying to show a picture to just give you a visualization of how it works. So this is, what is a solar flare? At least by now you would have heard of it. So what is it? What do you think? What is a solar flare? And how it may look in X-rays? This is not an X-ray image, by the way. It is from SDO AIA. It's called. So what is a flare? Whatever you.
Plasma is a negative.
Okay, that may be a CME. It's okay. That may be actually a definition of a CME. Correct. So that is pretty much the definition. So it's explosive release. It's sort of a very easy definition to go with. The actual definitions and the different variations of the definitions, but it's an explosive release of energy causing sudden brightening. So that is a bright flash. So what is the literal meaning of a flare? If you just flare up, or someone is flaring up, or light a flare. So don't even take the solar context. So if it's a flare, means sudden, you lit something, there's a sudden bright source that's coming about. And in the solar context, if the explosion, so think of it as an explosion, and that explosion is resulting in multi-wavelength emissions across wavelengths, and it's sort of like a bomb blast, I should say. And that bomb blast is not what I'm talking about, as is mentioned. That is this associated part, that is the CME, but that eventually has a side effect, is the emission of radiation. That emission of radiation, like so, as shown here, this is shown, this brightening is due to the wavelength that is seen here. It's the UV wavelengths. That emission is what we call as solar flare. And this brightening is, it's extremely bright. To quantify things in terms of solar flare, it's 10 per 30 ergs per second. So of that order is what we see. So, but to give a flavor, we will see how energetic these are based on when we try to quantify exactly. But for now, the working definition we can take from this is, it's a very explosive energy release, and it's a multivalent phenomena. But why are we looking only, or trying to look only in X-rays? So that is where this picture comes in. No solar flare lecture is ever complete without invoking Shibata et al. This is the, to my knowledge, this is sort of the standard for the initial explanation for a solar flare. So it's a simple concept. This is the cartoon for it, given by Shibata in 1995. So there is something called magnetic reconnection that happens in the corona. This is a flash point. So think of it as a flash point. I would only say magnetic reconnection as a process that converts magnetic energy, somehow pushes it into plasma, and generates a lot of kinetic energy for the plasma. So that's one word answer for magnetic reconnection, but there is a lot to it usually. But yeah, at this point, yeah, we will stick to reconnection. So as a flashpoint in the corona, which will actually generate a plasmoid kind of thing here, and then there's a burst. So it reconfigures the magnetic fields on at this point, and then there's an injection of plasma on the other side. So basically on this side and this side, you see the streams of particles, ionized particles, charged particles in the corona, streaming down and up. And this point, if it extends, if it gets cut and then extends, as he mentioned, that comes out to be the mass ejection. That is the associated phenomena called coronal mass ejection. We will not talk about that because I'm sure it is covered extensively in the previous lectures. So, but we'll stick to the associated brightening or the emission that comes about. So when the flashpoint occurs, let's say reconnection occurs, then the flow happens and there forms the energization happens for the plasma so that it will emit in hard X-rays. This is the hard X-ray loop top source, and then the plasma same plasma, when it streams down, as shown in the arrow mark, these are the chromospheric foot points or the photospheric foot points, and that is where the plasma energy gets dumped, and that is where from the another sorts of hard X-rays will come. And the entire loop, when it gets energized, emits in soft X-rays. So how soft X-rays are emitted and how hard X-rays are emitted, we'll come to that. That is in the mechanisms part. But for now, stick with me to the definition that this is the initial bright point. So it is not just this that is happening in only X-rays. As I mentioned, it is a multivalent phenomena. So a more detailed picture that evolved about is this. Don't get stressed out by so much of these at this point. This is the same picture that I tried to show you previously from Shibata et al. Essentially in a more colorful way, that the reconnection inflow is happening and then the outflow is going out, and then the plasma is going in. And once it happens, you see that there are several layers and several phenomena that are occurring. The associated phenomena that are there, we can see, are not only in X-rays, but at different temperatures. As it streams down, you have to always invoke that you're going through different regimes of density and temperature. So any plasma process from now on or in corona, if there's a plasma transport, it always is associated with, so yeah, it is like going through different lanes of traffic. If I'm changing lanes or going through, then you'll see that the speeds can change and the number of vehicles can change. So number of vehicles can be analogous to number density, and the speed can be analogous to the temperature, right? So it's sort of it's a very coarse analog, but definitely it is, and we can do that analogy here. So as the plasma streams down, you'll see that it passes through different temperatures or regimes of temperatures, which will brighten up as they come about. So 10 power 5, you'll see UV loops, and 10 power 4, you will see H alpha, and so on. And eventually, not just this, I'm sure there's a extensive coverage of the talk when on microwaves and radio waves, maybe tomorrow or day after, when Dr. Oberoi, I think, will talk extensively about how during this time, or the flaring time, this is what we call as flaring time, we will see that there are associated microwave emissions and radio emissions as well. So let me not go towards that, but it only will suffice here now to say, associated with this initial trigger of reconnection, you'll see hard X-rays, and then subsequently you'll see soft X-rays, and then all the other wavelengths associated with the solar flare. But to give a sort of a theory of what the solar flare is, this is an overall picture coming from the entire observations that have been done till now in all the wavelengths possible. Is this that there's a trapped magnetic energy in the corona, and that gets released, and that is released into the corona, into the energy, into the plasma, and that energy is transported by the plasma into the different regimes or heights, and the evaporation part is when the energy dumping happens, and when you hit, it's like let me say, it's like sputtering, something like sputtering, so ion sputtering. So if you hit or let's say even firing, if you just fire bullets at a with huge muscle gun, then you'll see that the matter will get sputtered, and so it just it takes a lot of energy of the bullet or the trajectory. So that is what is happening as evaporation. So it is the energy dumping that is happening here as it happens in the what we call as chromospheric downflow, and from there will be a lot of emissions. You dump a lot of energy, you'll see a lot of radiative signatures of the energy, and eventually the loops will cool, and then that's how the solar flare comes down. But how does it look when in terms of an observational signature? That is why this plot is put. As I said, this is, by the way, so I have put operational definition here is when do you say that a flare has happened? So what do you look and say this is a sign? So GOES, I'm sure this you've heard of it, geostationary operational environment satellite. Satellites, there are actually a series of satellites since 1974. They have a X-ray monitor called XRS, X-ray sensor, and it does broadband band integrated irradiance measurement for in X-rays. It always constantly looks at sun, and the operational definition is when you see this kind of a signature. So this sudden rise is due to the impulsive phase. I mean, we'll talk about different phases of the flare, but if there is a sudden rise and a short steep fall, so this is where the heating is happening. I would say the heating of the coronal loops, and then the decay, slow decay and cool off of this is happening. So when you see such signatures with a certain background above, I mean with a certain significance above background. So you can see the classification here. So I have separate when we go to the measurements part, we will discuss it, but separate slide on that. But right now, take it from me that yeah, if we see, if GOES says there's a flare, there's a flare. Right now, that is it. And that is for the purpose of, yeah, why is it operational? If you want to operate like a satellite or so from space for the purposes, if you want to tell the community or the world that yes, there's a flare that has happened, you just say that there's a spike in it, and then if you go to the peak of it and find the intensity, then go to there's a classification. Yeah, I'll talk about it if you already don't know. And say that this has happened. So this is some X 1.5 something flare. So they will report that this is the X. And you can see that this, not just this, even all of these are flares. So there can be different types of flares, and this is 1 month plot of April 2002, which is it's one of the peaks of solar. It's the peak months of solar of the cycle 23, and then you will see that there's a lot of flaring activity happened, and yeah. What one can do with this kind of data, we'll also, I mean, we'll discuss that. But yeah, I think we have digressed a bit from. So this picture essentially is told from one of these after synthesizing these observations, but not just these. There are several other measurements that come in and gets folded into bring up that picture. What are those pictures that we will see here? So if you just see the GOES X-rays, so this is soft X-rays. So GOES gives this curve. This is the light curve or the time series plot for time series versus intensity. So in astronomy you call it light curve. So this is plotted across wavelengths. You can see that different signatures are there in different wavelengths. So hard X-rays seem to be very spiky and short-lived, and then you come to the radio. And this is this is a quintessential picture that anyone should be dealing with from Arnold Benz. So multi-wavelength observations of a solar flare. What will they give us? I mean, what the story that we just told. There's a heat. Essentially this story. I don't want to repeat it. So this essentially comes from the science of observations of these. You'll see that eventually hard H alpha also gets triggered as low as H alpha. You start from hard X-rays and then even go to the radio waves and the metric waves, and you'll see the similar signatures Not exactly the same ones, but yeah, you have different time scales for each of these wavelengths. So the time scale and the study of these is what I talk about in X-ray timing. We'll come back to this plot in the X-ray timing studies, and then see how they can be changed, how they can be studied, and then how we can bring out an overall picture. That is what I wanted to go for on this slide. Then, yeah, so we've mentioned that the phenomena is solar flare, essentially the coronal phenomena that are happening, especially in X-rays, can be studied is the solar flare, and then we saw that lot of wavelengths also are included. But which wavelengths are included and what wavelengths will come about will from the observations. We can only get a sense from understanding what, or estimating, or preempting rather, what can be what will be the process that is. So that brings us to the part of, it is essentially the atomic physics. So let me start by saying, you are seeing an emission, or are you seeing an absorption? So what am I showing? Are these I mean, there are of course emissions, but are there any lines? When I say there are lines as in emission lines or absorption lines, so are there any absorption lines here? Any guesses? Like in optical, you would say yes, there is an absorption line somewhere, or you would have done optical spectroscopy in your, maybe in your MSc or so. You'll start to see simultaneous bright and dark patches, Fraunhofer lines, and so on. So can you relate to that physics here? Or is the same analogy of lines applicable here? We are talking about wavelengths from, or let's say energies from 100 eV and beyond, or even lower if we go to 10 eV. So we are, let's say we are in UV and X-rays. So how does the transition, atomic physics wavelength transition happens in terms of its, in terms of the observations? So as I mentioned there, the optical depth, that is the critical parameter. So absorption happens if it is optically thick, and if there is some subsequent dip because of a particular line that is absorbed, energy that is absorbed, right? But here, as I mentioned, we are in optically thin region, no lines, no absorption lines, all are emission lines. We'll have a slide on what sort of emission lines you can expect. But before we go that, it is essentially emission lines. So how does emission line come about? It has to, an ion or atom, be it neutral or ionized, it has to excite and it has to de-excite. Once the de-excitation happens, and the de-excitation must be radiative de-excitation, that is where I said radiative decay. It can de-excite and also not give out a photon. We will not see the signature. We will not see any line, right? So when it happens as a radiative decay process, we will see the line. So essential critical, I mean, this is physics 101, line emission 101 is that you need radiative decay after an excitation. And what possible excitations that are there? So first, the atoms have to be excited, right? And all of it in the subsequent slides, whatever I'm showing here, are essentially the processes that one can visualize or one can have, guided by the quantum mechanics that we know, allowed by the quantum mechanical principles, that are possible lines that can be generated from all the different types of excitation. The first one is, or the major dominant one is, the collisional excitation. Now we have to keep in mind, we are always looking back to the coronal densities and temperatures. So with that in mind, we will look at it. It is not like we are in the lab trying to generate this. So these may not be possible. These excitations and transitions may not be possible in lab at times, because those density and temperatures aren't available, right? So first is collisional excitation. So when an ion interacts with an electron, it's almost like a scattering by collision, and it has to be inelastic. why it has to be inelastic? Any guesses? I'm saying excitation is to happen for the de-excitation for a line, and it has to be inelastic, right? And I'm sure what this is the equation. So an ion is there in its plus m ionization state, and the suffix, the subscript actually gives the level, electronic configuration level. So I is, let's say, think of it as the energy level in which the atom is or ion is. So there is an ith energy level, and it is m ionized. So m plus ionized is basically it has lost those many electrons. That is the usual convention, right? Where it is, yeah. So this equation is not new. So when an electron, so we are in free electron space, because in corona we have the temperatures are high enough that electrons and protons are separated, they're not tangled together. So it is a free electron when it interacts with an ion, and it's an inelastic scattering. The energy gets exchanged, and the ith energy level of the ion goes to jth energy level with the same ionization. There is no change in ionization, and the energy goes from E1 to E2. So what is happening essentially when I say inelastic is that there is some exchange of energy, right? The incoming energy, if E1 is same as E2, then it is just, yeah, nothing's happening, it's elastic, and then everything's good. It's just maybe they would have changed the momentum, not the energy, right? And the critical part here for the ion, so ion has to be excited, right? So what we're saying is a line, the ion gains energy, so E1 must be greater than E2. That's a critical factor here. If E1 is less than E2, then the ion actually gave the energy, it actually de-excited. So inelastic ion electron scattering or collision is the main contribution factor for all the lines that you see in the corona or transition or chromosphere. Why not other ones? Yeah, that is because of their interaction cross sections. So each process will have a particular interaction cross section or probability, let's say. Not yeah, probability is a better word for it. Based on the number densities and the probability of this event happening, and given the energies that are there. So if E1 is not able to give energy and come down to E2, then there's no excitation and then no subsequent de-excitation. And then this second one, it's an interesting one. Maybe you might have heard of it or not, but dielectronic recombination is another process which also is pertinent in the coronal domain, in the solar coronal domain. So it happens like so. So you have an ion, and then there's an electron that comes about. The interaction happens by recombination. So basically, the electron is captured by the ion. So what happens? The m plus 1 goes to m plus m. This one electron has come back, so that plus 1 goes away. At the same time, the I changes to j. But this is not it. There is also an intermediate where is a dielectronic thing coming in. So when the electron is getting captured, part of its energy is sent to the bound state of another electron, which within this ion. So there are several electrons that would be there within this ion, and one of the electrons is getting excited, but not getting ionized. It's not getting a free electron. So it is changing its bound energy by taking some energy from this. That is an interim state where there are two electrons that have just come in. One is the incoming electron that has been captured, and then there's a bound electron that has just gained some energy. That is a metastable state. It only stays for some time, and that when it de-excites, again the de-excitation can happen non-radiatively as well. It can also come back. The excited electron, the second electron can come back to its ground state, and by giving back this electron the E1, then there won't be any emission. But when the emission happens radiatively, de-excitation happens, then you will be left with this, and that forms another line. So all I'm trying to say from this is there are different processes at play, not just the ones that are simply there, and different forms of collisional excitation or ionization. Okay, I didn't take the word ionization yet, but there are. So how is ionization different from excitation? It has to be clear, right? So I have always been talking about excitation, but it can also get ionized. Correct. So excitation means the ion still stays with the same electronic configuration of whatever. If it is 3+, it will stay 3+. Just that inside the electronic configuration of the orbital configuration of electrons has a different energy. So the phase, if you go to the wave function, the wave function will have only an extra part of the total energy will remain the same. If it has to be conserved, but it's only that the energy will have now an extra change in the term of electronic configuration.
Then the ion electron method as it is explained by the collision has to be inelastic, because in elastic collision say that the energy is not conserved but the momentum is conserved.
Yeah.
Whereas in elastic collision, energy can be transferred but it has to be conserved. So here you said that the energy has to be conserved, but it has to be the electron has to give energy to the
Energy. Yeah.
So that doesn't really imply that the collision has to be elastic.
Okay, so you're saying okay, when I say it is in terms of scattering or so there is a slight distinction between inelastic scattering and elastic collision. So the classical picture of scattering doesn't apply to the collisions part, I guess. So here, okay, take it. When I said inelastic, I mean that the energy of this incoming particle is changing. It won't be the same, and so is momentum. That is pretty much I wanted to say from this. Had it been elastic, the definition what I would invoke is that this even will still be even. You are saying that the exchange of energy will still be there in terms of
normal.
that is like the scattering part. So when you say, yeah, for a classical picture of, let's say, two balls colliding, that is true. But yeah, when you come to the part of the collisions and ion electron plasma collisions, you'll see that yeah, there has to be change in energy. Sorry, oops, I jumped. Yeah, so the dielectronic recombination is that process which gives us a metastable state, and then eventually has this leaves the ion with this part, and that is where the radiative de-excitation can happen. It is also one of the pertinent mechanisms that is there. That is why I brought it up. Otherwise, in normal in laboratory, we don't see this because the conditions are will not be feasible. It will be very tough to regenerate what's there in solar corona. And then, yeah, so the question where I stopped, or the part where I stopped, was there can be ionization as well. When you impart an ion certain energy, the electron can take and just become a free electron. No more attached to the ion. That is when the ionization happens. That also is a form of excitation, provided if it recombines. That is why I'm writing everywhere ionization with recombination. When the recombination happens, it need not essentially come back to the same state. So it is a form of an excitation. It is like how you gain energy. I gain some energy and then I'm losing less energy by doing some other stuff. So the net is a gain. This is that part. So you're seeing for a net gain, only then the ion or the resultant ion will have a enhanced energy level from which it can de-excite. So first of those is photoionization and radiative recombination. And then we have collision ionization. It is same as this part, but the collisions can be from electron ion, proton ion, or ion ion basically, or even photon ion. Photon ion is a photoionization. And how do they recombine? Yeah, that's very interesting. So it has to recombine and get to an energy state, so that I have the processes in the next slide. And the third one is, it's an excitation ionization and the dielectronic recombination. So we'll invoke the recombination process that is shown here, and then there's an excitation ionization that comes. And not just these. Yeah, we have mentioned that there will be a background emission from the bottom layers. See, if you're in corona, then you'll see that there's photon emission from photosphere, chromosphere, transition region, all of these. And if you expect a black body which is in let's say near thermodynamic equilibrium, then you'll see that there will be some amount of photons that are coming even in X-rays. It's just a continuum, right? It's just the Planck's function that goes about. So So those photons, they're actually photons coming out. There can be some X-rays or even UVs. They can interact with the ionosphere. Though I said optically thin, that doesn't mean that there is zero interaction. Thin means it is very less, so the amount of interaction is less. So the I by I naught is close to 1, but it is never 1. There will always be a loss. So we have to, yeah. So these interactions can happen. So we will get classical fluorescence. So fluorescence is when photon interacts with matter, knocks off the electron, and then that is that energy is actually recombined, and then you emit a photon again. So it is incidence is photon, matter interaction, output is a photon. But this time the output of a photon is a characteristic wavelength. So if I hit it, hit wood with an X-ray gun, this let's say I hit this part. So mostly if they're carbon or what does wood contain? Carbon, nitrogen, oxygen, probably. So there will be characteristic lines from oxygen line, carbon line, and nitrogen line. Of, let's say, mostly X-rays will give K alpha. Yeah, I hope you remember the Lyman-Balmer series and so on. So if the transition is from 2 to 1, 3 to 2, and so on. So if the transition is coming to the first orbit, then you'll see it's Lyman series, and then that is what we call as K alpha lines, K lines, or alpha, beta, gamma lines. So mostly you'll see the fluorescent lines. So actually we'll see fluorescence of atmosphere. That is what I'm coming to. Even that is true for anything. So Earth also fluoresces. I hope. Yeah, again a bit of digress. Did you imagine that Earth can actually be fluorescent? So the fluorescence is not the optical fluorescence that you are thinking. The energies of these will be again X-rays. Fluorescent material is not the green light that you think it is there, but that is another process that is happening in optical wavelengths. It is another form of phosphorescence at different times, time scales. But then X-rays, when give out again X-rays, characteristic X-rays, they emit in the soft X-ray region characteristic to that element. So each element will have a particular energy, and so when solar flare is emitted, it hits the Earth, right? Where does it end? I mean, any guesses? Okay, so total digression, we are coming to Earth now. This solar terrestrial physics. So when solar flares, all the solar X-ray photons are coming in, and when they hit the where do they hit the Earth? No. Aurora is happening because of the magnetic, CME, but yeah, it's happening because of the magnetospheric process within the Earth. It is, a punch is coming from the sun, but it itself is generating aurora. It is not the direct, it's a consequence of it. But where do the X-rays end up? I'm getting okay, yeah, why go to space for X-rays? So okay, now you will answer the question. So atmosphere is opaque. Yeah, so when I said optical depth of corona is all less than 1 and nothing happens, X-rays can come out easily, optical photons can come out easily, but not the same for Earth's atmosphere. Earth's atmosphere it has a density profile, temperature profile. When you draw that, you'll see X-rays can interact, and they do interact approximately at the bottom of the ionosphere, at the E region or F region. If anyone has done ionospheric physics in their MSc classes, then you'll see that around 90 to 120 kilometers altitude, you'll see that the X-rays will hit. So all the solar flare X-rays that come about, emitted in the interplanetary medium, when they reach the Earth, they get stopped there. And once they do that, you get emission lines. That emission lines are the fluorescent lines of Earth. So what are the fluorescent lines that you can expect from Earth? This is just to get you going in terms of what is fluorescence and all that. So what will be what are the fluorescence lines that you can expect from Earth? I go up, take a spacecraft. We have spacecrafts. So we look at Earth. Instead of sun, I look at Earth in X-rays. What are you expecting? Yeah, it is. I mean, it's totally off the topic, but yeah, it is. It can be categorized as, we'll say, we are going to solar terrestrial interaction. What do you expect? Any guesses? Yeah. Planetary X-rays. I mean, I already gave you the hint that it is just fluorescence. So fluorescence is So there's a continuum emission. Solar flare will have some, let's say 1 to 10 keV, all wavelengths are coming. Okay, I gave a lot of things away, but yeah, definitely some few energies are coming. What do you expect at when I look at Earth?
Whatever the water.
Okay. Okay, but yeah, so you mean to say atmospheric water? Because ocean. Yeah, X-rays won't reach the ocean. If they can reach the ocean, we don't have to go to space to look at X-rays, right? All the X-ray observatories are space observatories. For the same reason that you mentioned, that atmosphere stops the X-rays, so we can't detect them on ground or on water. So what is it? Yeah, it is basically, you'll see the lines of atmospheric composition of Earth. There is, looking at Earth, when we turned back, we had an X-ray spectrometer on Chandrayaan-1. We looked back at Earth during some, without pointing at sun. What we found is we saw an argon peak. So argon line is coming from, yeah, because of the constant atmosphere has the constant of argon in it. Be it neutral or ionized, it doesn't matter, because it has electrons and the transition happens from electronic transition. So we saw argon lines. So yeah, that is some totally a digression in terms of X-ray fluorescence, because I spent a lot of time in fluorescent spectroscopy. That's why I got carried away. But nevertheless, the point is, yeah, you can actually fluoresce anything. Even you can see the fluorescence from this also. You'll see the constituent material. So fluorescence, X-ray fluorescence, for the instrumentalists, X-ray fluorescence is used to find out the elemental composition of any unknown material. So if you give me a fossil or something, some unknown material, shine it with X-rays, see the spectrum, we can find out what it contains. It is a non-destructive testing method. So without actually breaking it or doing some chemical test, this is one test. It's totally an aside. Anyway, let's move on. Yeah, so the processes that I mentioned previously regarding the ionization and recombination are shown here. It's just a recap of the previous slide, but in terms of equations. So photoionization is capture of photon, and then electron will be emitted because it ionizes. So electron has to come out, and then the ionization state of the ion changes, and then at the same time it has to recombine, and the recombination will give you HD. I mean, it may sort of look like what is it, a zero-sum game, what is happening, but yeah, this can actually be some energy, and the recombination will give out this. That is one of the ways in which this can happen. Collision ionization, again, you're having when it collides, it's not just excitation, it is giving out another electron. So there are now two electrons that come about, and now there is a process, interesting process called three-body recombination. It eventually leaves out the first incoming electron with a different energy, and then the first electron that's captured, the E2, will be captured back by the ion. So all of these will have the commonality of something, the state of the energy state of the ion getting changed, and that is leaving it into a different state, not necessarily a higher state. So if you just put the energy such that the E1 is greater than E2, then you will end up with the state that the ion is actually becoming more stable. So it is going down. So all of this will actually result into an abundance map. So yeah, and the third part, I mean, it is excitation, ionization, and so on. It is one of the other processes. But so what we can get from all these processes? There are lines that will be emitted. These are the so if we go to yeah, each ion and then find out what is the probability of interaction, basically the factors. You have to solve this equation write the Schrödinger's equation for the system, and then solve for it, and then find out the wave function and probability of it. So that's very easy for me to say, but yeah, believe me, it is very tough. So for this, there's a dedicated atomic database called Chianti. It is not an Italian restaurant. Here we are talking about a database, atomic database, which actually does all the computations for us with respect to the solar coronal abundances, and then gives out the probabilities of these reactions happening, by which we can do a line flux estimation. Now imagine we are sitting at some point in space from a d distance from this star, which is the sun. So what all things you have to factor in are these. So for you to find the number of emitters per unit volume, or let's say density of the emitters of a particular ion in a particular energy level, you have to fold in all these factors. So it is not daunting or confusing. I'll try to split them out. That's why I have given in this way. This tells us the relative ratio of this ionization having different energy levels. So jth energy level is what percentage, and this is the relative composition of relative percentage of how many of total of the X atoms, how many of them are in the mth ionization state, and then of the total coronal abundance, how many of them are there with respect to the hydrogen. So you take this as, let's say, carbon or iron. So iron 10 plus. So iron 10 plus is in which energy state? At jth energy state, what is the probability? Iron 10 plus versus total iron in corona, what is the ratio? Iron ratio versus the hydrogen ratio, which is the basis, the primordial. Anyway, primordial, it is not the primordial. Sun is a second generation star. So the abundances that we see are not primordial abundances. They are. So why do we see iron? Again, yeah, this is a definite question. So do you expect what iron atoms at Sun? I mean, you would have seen AIA images of from SDO also previously, yeah, in EUV wavelengths. So what is that? What is causing that emission? It would be told that it would be coming from some iron line, iron 14 or iron 16 or iron 10 or iron 8. So what is that? When you say iron, it has lost those many electrons. It is singly ionized, triply ionized, so it's 8 plus is that those many electrons are gone. So when we say that, when we are saying iron, so it means that there is iron in the solar composition, right? How do you expect that? I mean, do we expect iron, or for that matter, what all elements that are there? It is not just a ball of hydrogen and helium. All these lines actually that I'm talking about, that we will show, are not exclusively from H and He. Carbon, even iron, calcium, silicon, all of the elements up till Fe, even heavy ions also you can see. So all the lines, because if you solve for an iron atom that is hydrogen-like, it means it is stripped of all of its electrons. 26 of all of its electrons are gone. So it's iron, 26 or H plus, if you say, for that matter. So that when that much energy is pumped onto the iron atom, all the electrons are stripped off, then it is like in a hydrogen state. It's just a bunch of, it's a proton-like, but its nucleus is not proton-like, right? But its electronic configuration is proton-like. That is what I mean by H-like or He-like. So those, when you put in the equations, Schrödinger's equation, quantum mechanics equations, that you will see that their energies actually fall in X-rays. So the ionization needed, the transitions of, let's say, iron 25. Iron 25 is 24 times ionized iron. So 24 electrons are gone, stripped off. So those, when it happens, when that is plus 20, M here is, let's say, 24, 25 for that matter. What is the and that is the stage at which it is residing. Then it has to de-excite. When it de-excites, what is the line that one can emit? Those lines actually fall in X-rays and subsequently. So all the UV, extreme ultraviolet, and even soft X-ray, and the lines in the even up till let's say 6 kV or 7 kV. That's the highest we see lines to. So those are coming from very high elements, heavy ions, or so to say, and very highly ionized, massive ions. I have a spectrum. Don't worry how it comes about, but this is the split of the contribution factor, and you put all of it together for a given temperature and atomic number density. Net flux that you can observe at the distance scaled by 1 by d square will be this factor times the Ne square dV, and Ne square dV is famously called emission measure, or the essentially the driving force for any of these. So this is coming from the database. From this Chianti will tell you, put in the T, this Ne, it will come. So now if the volume is changing, the volume, coronal volume or the loop volume is changing, or the density is changing, then that is what actually brings about the evolution of the flare. So emission measure is something that is a derived quantity from the solar X-ray observations, especially the spectral observations. We will come to that, but yeah, it is suffice to say at this point to that the flux, the line flux. What am I talking about? We are talking about line flux. There will be a lot. So imagine, so there will be a lot of lines, because there are a lot of combination of states possible. All of these, so that it can be multiply ionized, it can be in multiple energy states, and it can have multiple elements. So there are too many elements. Yeah. So to answer your initial question, it is not the primordial abundances. So if you consider galactic abundances, or the primordial what we say the initial post ionization epoch abundances, they won't match with the photosphere, because it is sun is a second generation star. It means, yeah, basically it is formed from the remnants of supernova of its first generation stars. So when a supernova of previous generation stars in Milky Way happened, they would have automatically, by virtue of supernova emissions, it means that there would have been formation of heavy ions, heavy elements, and in fact even up to maybe osmium also. So you can find really exotic elements in that, but that is how even iron. So I hope you have basics of stellar structure and evolution. So for iron to form, you need very high temperatures, and the star must be in its advanced stage of evolution. Otherwise, it is a step-by-step process, right? Hydrogen to helium and CNO cycle and so on. So further, for you to reach the Fe, yeah, it has to be an advanced stage, and from there, if an emission or if an explosion of supernova happens, from there the supernova remnant will have these abundance configuration, which actually when it is coalesced together, so our cycle. I usually say that our solar system is actually a recycled solar system from some previous systems. So that is why it doesn't have its initial primordial signature. Yeah. Anyway, to come to this point, that is how we see. Okay, did I miss one slide here? Maybe I have. Yeah, I have a spectrum. Please hold on to it. So the fact that line flux can be estimated from this point using all this, but we need a database. Otherwise, we have to do our own calculations and feed in. So what is essentially done is you invoke the temperature, and try to find out for a number density, find out what is the G factor from the database, and try to see whether it matches your observed flux or not for a given energy. Then we have continuum emission. What is continuum emission? Line is just one line. It's a Dirac delta. There is only one energy. Of course, it is never a single energy. It will have a natural broadening because of different factors, because of the smearing of energy levels at the atomic level itself. Also, there will be something called Doppler broadening. Sorry. So Doppler will give you a broadening, so the line will actually look broadened. And also so all of these will lead to some kind of a smearing out. I will show you the lines as observed, but yeah, for now, what I'm trying to say is continuum emission will not look like it. It's an analog thing. All energies are possible. So why all energies are possible and how? And this is where much of the hard X-ray and X-ray spectra we live. So basically, people doing high energy physics, high energy astrophysics will live in continuum. Much of the time we live in continuum because lines will not be available at high energies. And mainly two types of mechanisms are responsible for it: free and free bound. You have heard of free emission, I guess, before. Its other name is Bremsstrahlung. So free emission is when just the name is coming from the fact that the interaction with an electron ion, it's a Coulombic interaction, and when it happens, the energy of the ion, the electron changes, and by the virtue of its change in energy, some emission is happening. It is basically Bremsstrahlung in German translates to some breaking of it. So if it is electron is getting, so it's not broken, it is the vehicle breaking. So if it, as it veers about an ion, the Coulombic forces are at play, and then that changes the direction and the energy, thereby emitting a photon. So those photons are all mostly multi-wavelength, spanning all wavelengths, and for us at these energies at which the electrons are, we will see a lot of X-rays emitted due to the free emissions in corona. So, and all energies are possible here. There is no limit on to what energies one can take. So E1 can go to E2 any energy. So that is why you'll get every possible energy. That is why it will continue emission. The other mechanism is a free bound emission, free bound radiation. It is not. It is the other part of it when the electron is captured, and then it de-excites and to form a photon. So it's a capture of electron. It's no more free, so it is now bound to the ion that it is interacting with. So this is the energy balance that is for both the mechanisms. The incoming energy of the electron is a telling factor, and the outgoing here for free, and EI is here is the energy at which this electron will eventually settle down into the ion. So the electron, when it gets bound or stuck onto the orbitals of the ion, it will have an energy that is EI. So the rest of the energy goes to the photon. So these essentially, if you look at X-ray spectra, you'll see lines and continuum, and the sum of it is what we see are coming from all these processes. So when you, so I mean, the run up to all the X-ray spectra observations is pretty much this one. That for you to see an X-ray spectra, what are you expecting? You are expecting a lot of lines that are coming from the line emissions that I'm shown here, all the mechanism that I just listed, and the continuum emission that is happening. So that's part one. I hope we can take a break. Yeah, so yeah, we can stop. We'll move to the next part soon.
So we were talking about solar flares, and you said that solar flares themselves, they are made up in the active region where the magnetic field lines connect and reconnect. So we also see CMEs over that region. So can we use solar flares as precursors of coronal mass ejections?
Yeah, so that's yes, one can, but there are CMEs without flares and flares without CMEs also. So
yes, sir. So is there any connection? Can we use solar flares?
In fact, initially when this observation started, maybe in even 80s and 90s, when first coronal observations or eclipse observation happened, then they thought they are just both. I mean, they initially were different phenomena, same phenomena happening, flare is CME and so on. So the distinction was blurred. But later, as we accrued more observations with coronagraphs like from SOHO and stereo, and we have continuous X-ray flare observations, we see that there are associated phenomena coming from the same coronal region. So when it happens, of course the association is there, link is there, but how it is essentially, one is a mass ejection and other is radiation emission. Yeah, that is true. We can associate them, and then there's a lot of science, lot many papers that you see trying to correlate or associate the CME and flare thing. And one of the science aspects or science goals of SOLEX is that CME flare association. So yes, one can do that, but we have to keep in mind that yes, CME, for you to see the CME, it's a mass ejection. So you have to have, there are many CMEs called stealth CMEs. You will not see them at all in coronagraphs. But if you are somewhere there at Venus or so stationed, you will see a plasmoid, a huge plasmoid has come about. So, and there's many times you'll see small flares, there is no CME. All the small flares cannot be associated with the CME, maybe because there is not much plasmoid energy density that is there. There may be a plasmoid emission that is coming about. Yeah, this classic picture is plasmoid emission. So if the filament gets cut and then this goes up, it can always lead to a CME, but whether we are able to detect that, can we call it a micro CME or something? So whether is it lost, it gets lost in the heliosphere and will not reach Earth or the vantage point. That is something that is to be considered. And also the angular width. This, not all CME, yeah, few CMEs can have very large angular widths, even up to few 120 degrees or so, or even entire. I'm not sure if it can span the entire azimuth, solar heliospheric azimuth, but definitely, yeah, there must be the sensitivity to detect those. But flares, because they are X-ray radiative signatures, if you build an X-ray instrument that is very sensitive, you can detect flares, even micro flares, nano flares. I mean, we will talk about those, but yeah, they are associated now, but they are considered two distinct processes and phenomena happening almost at the same time. Yeah.
Also, we talked about our sun being a second generation star.
Huh.
So, is there any way to know if a star is third generation or fourth generation? Because we said a star is second generation. What if a star was born from 3 to 4 stars that died before?
Right.
Do we have any?
Yeah, that depends on the time scales. So from the time that the galaxy is formed, so you'll have a birth date for the galaxy, right? So yeah, so evolution of the galaxy to form particular stars will take certain time. From the primordial matter, intergalactic matter, to stars, that will take a process. And for the stars to evolve from main sequence to, let's say, go to red giant stage or die and eventually come out to be, eventually turn out to be black holes or so, that will take some stage, or become AGNs or so. So that time scale, this formation of stars time scale and stellar stars formation to death time scale should add up, and then see currently where we are at. Let's say from Big Bang, or let's say from, we will see that, yeah, just we are in the second generation. For the third generation to happen, yeah, stars would have had 2 cycles. Yeah, right. So one cycle of main sequence itself will go, yeah, how many years, right? So it's in millions of years. So depends on the size of the star. The massive star and the more luminous the star, more quickly they evolve. Slow. So yeah, essentially you are looking at stellar evolution. So time scale of stellar evolution will hint at which generation and add up the total time, not the total time, the time from which we think the galaxy has formed. So when you add things up, you will see that, yeah, it is sort of it.
Thank you.
Yeah. Yeah, so when the simplest picture of reconnection, you can think of it like this, right? Oppositely directed fields coming close to together, this magnetic field, the picture will, after some time, will become this, right? So now this is that region that I showed. It's a vertical region. Here forms that current sheet, where in fact the magnetic line's neutral line is there, and then current will actually form a place where it doesn't have to go there, it doesn't have to come here. This forms the current sheet, and where this mechanical energy, the heating happens. Why it happens, we don't know. Definitely the heating or mechanical energy gets dumped here, and then from which, because the field lines are reconfigured here, it will get pushed into this. And these pushing of that and a sudden burst of energy is what we can say as jet, reconnection jet. So that you can see even the upside also, there's a blue arrow, that is actually the push that is given to the plasma, the kinetic energy.
From where the jet is erupted, from the surface of the photosphere
No,
or
no.
in between the reconnection of magnetic field
Jet
lines?
is actually that push that I just said. Follow the arrow, right? It is so essentially this I have rotated and plotted it there. So when you see that, it is just a push down here. That is it is not in the photosphere. It is in the corona.
Sir, you call just CME, it confined mass. We can say that this mass is plasma.
Yes, yes,
But sir, there in this loop, there we also have plasma
yes.
in lower loop,
In the
in solar flare.
correct.
Yes, sir.
But that is bound to the magnetically bound to these regions. It is stuck into the internal structure of this sun. So the magnetic lines are connected, so it doesn't go up.
It is confined plasma.
It is it is on the sun itself. There is no emission. So
So
this is no more connected. It will just leave if given. It is like it is given the escape velocity to leave.
Sir, is it a frozen plasma or flowing plasma?
We consider it as frozen in the plasma. The assumption here is it is tied to the magnetic field and it is frozen into the magnetic field. The condition of frozen influx is it is debatable, but it is considered to be frozen.
Sir, this is the region where the X-rays are emitted from here. So, is there any difference between frozen plasma and flowing plasma?
Yes, definitely. Yeah, if it is magnetically connected, then you will say that when you say it is frozen, it is in line with the magnetic line, right? It is not moving about. So it depends on the plasma beta that is there. If magnetic force is strong, then it will just be held by plasma. But if it is not, like in the case of, let's say, energetic particles, these ones, some of them can gain energy and they can just
Sir,
get
how
away.
X-ray emission is affected by this in both of cases?
Okay, X-ray emission happens because mainly particles that are connected inside this loop are held and they are energized. That energy is getting dissipated as a radiative signature in terms of X-ray. So not the other way around.
Thank you, sir.
So you had spoken about the second generation stars, right? So so then that means in first generation stars, then you will not see much signature of iron or any of the heavier elements, provided that it's in
provided the primordial configuration. If there is no abundance of very high stars from which it formed. If it is just hydrogen, helium, or if it's just hydrogen, then you'll not see any of this time. Correct. Yeah, it can be done. Yeah, if you do some astronomical measurements which are first generation stars, you'll see they won't have these lines because obvious reasons. But the galaxy is too young. Right.
Sir, this sunspot and solar activity has any relation to the solar flare activity? Like do they increase with the increasing number of sunspots?
Yeah, they do.
And
yeah,
yes,
more sunspots means more active regions.
Yes, I just want to clarify this. But I have also heard this thing that a problem of coronal heating was justified with the very numbers of micro flares and all types of flares. Can you just explain on that? How is that? I just heard this. I don't know.
I'll come to that. We have we'll touch upon that anyway.
Thank you, sir.
Yeah. Part 2, maybe part 2 or 3. we have a long way to go anyway.
Sir?
Yeah.
Is there no X-ray signature from the plasmoid itself?
It will be there, but it will be there provided the energies are high enough. But as soon as the plasmoid is erupted, you'll see that the velocity of the plasmoid or CME in this case are very high, and then the density slowly reduces that you will stop seeing it. So what we call as there is a loop top. So the highest you will see is a loop top, and then to certain extent this point you'll see X-ray emission. Again, it depends on which energy band you're looking at. Soft X-rays you may still see, but if it comes out of corona and go to let's say 2 to 3 solar radii, then I don't think the densities are sufficient and temperature will be good enough for enough X-ray emission.
Another question, you talked about free bound radiation, in which ion captures an electron, if I'm correct, and releases radiation.
Yes.
So usually, I mean, from the point I studied it, we call it line emission. I'm not sure why you said it was continuum emission. What am I missing there?
Yeah, so line emission happens from all those processes that I mentioned.
Uh-huh.
But if there is no restriction in terms of the energy exchange,
Okay.
so it depends on the incident kinetic energy of the electron.
Okay, so bulk, you're talking about bulk interaction, is that so?
Not really,
Okay.
not really. So what is constraining here is the E1, right? So if there are different,
Got it.
you take Maxwell-Boltzmann, they
right.
not be even. It will be a Gaussian. You put it over and do minus EI, and EIs will not be EI. EI will be discrete EIs. Again, quantized levels. Put all of these together, you will see different Gaussians. If it is Maxwell-Boltzmann, it will come as a continuum.
Okay, thank you.
Also, if I may add, the fact that it is a free bond means it is not jumping from energy level to energy. It's coming from free, which means from any energy level it can come back to this boundless. So that means it can be it can have a continuous energy. That's why it is free bond. Next question.
Yes. The diagram that you have shown in Shibata-et al. Diagram, that how this go to that.
Yes.
side.
Yeah.
Yes. Here we see that because of this magnetic connection, there will be a upward streaming and downward streaming of electrons.
Yes.
And we can also see that there is a downward streaming of electrons in magnetic foot regions, in
Yes.
both regions.
Yes.
So I couldn't understand from where this X-ray generated, because of this deceleration of electrons or acceleration of electrons.
Correct. So you're agreeing, you're with me to the point that the reconnection is pushing the electrons to a different energy state.
Yeah.
Right? The phase space is now energized.
Yes.
Right? Not the phase space, rather the electrons are energized, so the phase space is moved. Right? So now if they're streaming down, they will face higher densities in chromosphere or photosphere. If they reach photosphere, mostly it is chromosphere. That is why it's called chromospheric evaporation. So when they hit that, they sort of, I mean, I don't want to use the word, but yeah, they see a thick target on which they will dump it. So the model that we invoke is thick target Bremsstrahlung. So when electrons which have these energies are going streaming down at these foot points, they have to dump the energy. That is when they dump that energy. How is the dumping happening? Again, by those two processes, free or free bond. That will give you a
Continuous X-ray.
continuous X-ray, and that is what the radiative signature of it is.
That is the continuous X-ray we have observed.
Correct.
And that discrete, that hard and soft X-ray.
So it depends. Hard and soft are basically the energy regimes, right? If the electrons, the kinetic energy is high enough, basically they are non-thermal. So non-thermal, we mean it is hard X-rays. Soft X-rays are mainly a residue or the byproduct of thermalization. So when the electrons are streaming, they also have to interact, right, with themselves and others. So there will be a lot of energy exchange during the transport. I've not come to the part. So when the transport is happening, there will be the energy exchange, and what is happening is the thermalization. So 1 million Kelvin plasma previously now is taking a lot of extra energy. Now it became 2 to 3 million Kelvin, which is making it emit in X-rays. Right now the X-rays, soft X-rays will be more, or rather temperature of the soft X-ray will be high. So you'll see an increased X-ray emission. So that is how the distinction. So I thought I will come to that part. So thermalization leads to soft X-rays, acceleration leads to hard X-rays. That's one line.
We can also observe this characteristics X-ray, discrete X-ray.
Yeah, we do. Yeah, fluorescent lines, but yeah, again, it depends on where we are, and if it is coming from this point, then again that X-ray, let's say ion line, it has to come about from that region, and again, depending on the optical depth for that energy, it can get attenuated or eaten away by the surrounding radiation. Otherwise, we will see the line.
Okay,
Yes,
so what I have understood is electron streaming downward, and they faces various regions. Because of that, they will emit various. They will emit the X-ray, which is continuous, and when they got reached or from the magnetic foot region, we observe that characteristic X-ray because of that iron, that highly ionized.
Yeah, characteristic X-ray is a fluorescence line. Right? That is a very small part of it because because of the density, and it should have again photons coming. Characteristic X-rays are coming from photoelectric effect.
Yeah,
Right.
So
that is not the main.
Rearrangement of that electrons on the.
Yeah, that is exactly. But that is not the primary contributor to the emission. The primary contributor is the accelerated electron giving hard X-ray, thermalized electron giving soft X-ray. Correct.
Thank you.
More questions?
Yeah, we will have another session. We can or we can break. Yeah. Anyway.
A bit about the emission of hard X-rays. I mean, accelerated particles in which process? I mean, the context of the process, is it magnetic reconnection or interaction with the magnetic field?
It is Bremsstrahlung, non-thermal Bremsstrahlung.
Okay.
Over. So, more questions? Okay, then we can take a break for about half an hour, maybe 11:30 or so. We can reconvene 20 minutes, and there is tea outside. Okay. I think you went into proper details, which is really good because that's what